All right, so homework B1 was due on Tuesday, so there's still the availability window open during the late period, so it's 20% per day. So as long as you turned it in before Wednesday at 10 a.m., then there'll be no late penalty assessed. Otherwise, there's this 20% per day, and then after the fourth day, then so on the fifth day, the assignment will disappear, and the solution set will appear. So the interactive Canvas activity for D1 is available due before lecture D1, and then homework C2 is available, but it technically isn't, released until the next lecture Tuesday. So that, so basically means that after Tuesday's lecture, you'll have everything you need for completing homework C. But if you want to try on it, you can give that a shot now. And those are two questions related to random number generation, which are covered in Chapter 7 of the Banks book. So you can look ahead to that, or you can do that, or just wait. The competitions, big thing just want to remind you of is if you're interested in the Rockwell competition, the registration is end of September. Their FlexSim, it's also toward the end of September. And then there's a Simio competition. I don't have info on Simio, but you can look that up as well if you're interested in those. And that's all I've got. So any questions about class admin stuff? All right. So last time we talked about the spreadsheet and different ways you could use it, and we showed how you could use it to simulate a simple MM1 queue. So this is as you take, say, 470, you'll learn this notation, Kindle's notation, but we're starting to learn about input modeling, and basically this M and this M has to do with the distribution you've chosen for the inter-arrival times, that's that first M, and the service times, that's that second M. And so basically in an MM1 queue, what you're saying here is there's one arrival process and there's one service process. The inter-arrival times are exponentially distributed and the service times are exponentially distributed. That's basically what that's encoding there. And I'm only bringing that up again that we'll get to this sort of later as to why this sort of stuff's important. But what I'm just trying to get at here is that when we model systems, we care about two things: the structure of the system, that's what you draw in Arena, and then the distributions that go in each spot of that structure. And so that is what's sort of capturing here. This is saying we've got one server, and these are the distributions of service times into arrival times, so-called Kindle's notation. So eventually, in courses like 470, you learn Kindle's notation, you learn all the letters that go into here, and effectively you learn a compact way to tell someone, to summarize to someone all of the input models you've chosen for the type of system. And in this case, you don't actually, this is actually describes nodes in a system. So when you talk to someone, you say, well, we modeled this as an MM1 queue that is connected to GM4 queue and so on and so forth. And so you're actually talking about little subsystems inside the system. So in this case, we're just focusing on this simple node here where customers arrive and one customer receives service at a time and other customers wait in the queue. And we did that last time in this example, which sort of matched the exercise that you do for the bonus of that homework B1. So I won't go through all of that, but basically, you put in these simple relationships between customers. And after you put in all of the relationships, the spreadsheet sort of snaps into place and all of the numbers match what you'd get if you would have done a hand simulation where you did from time to time to time to time. And so it's a different way of coding that up where you don't have a state variable that you're maintaining in your system, but you still get the same data out. And so that's for a simple MM1 queue. And so this is me just, showing that this is what it would look like for hand simulation, but you get the same data out here. So these numbers here, you can get by combining these numbers here, 1, 8, and 7, that corresponds to that 16. The 13 that customer 3 departed at, we can find the customer 13 or customer 3 departed at 13. It all matches up. So before we go, we want to complexify that to see what more can we do with that, and then sort of start talking about, well, that there will be, the reasons why we can't continue to do this for more complicated systems, but then pivot to things that spreadsheets are really good for, like Monte Carlo simulations. So before I get to that, were there any questions on this example where we did the simple MM1 queue in this kind of spreadsheet back here? Okay. All right, so that was our MM1 queue. Another node that we can describe in Kindle's notation is a so-called MM2 queue. And so again, I'm not expecting you to know Kindle's notation for this course. In other courses like 470, you'll have to do that. But I'm just exposing you to that it exists. And an MM2 queue describes a node that looks like this, where the input has got some arrivals, and those arrivals are going to be exponentially distributed into arrival times. But then now there are two servers. So you could view this, you might draw this in Arena as a single process that has capacity 2. Or you could sort of think, though, I could break it out into these two these actually sort of more like it would be in the physical space, and say I've got two servers working in parallel that are being fed by a single queue. That's what this MM2 is. And then one of the things that is not specified here is what the dispatching policy is. And so that's, when there are both servers are available, who gets the first customer, the next customer. And so we can say things like, that whenever they're Able and Baker, we'll just name them A and B, Able and Baker, whenever both of them are idle, if there's a new customer, we go to Able first. So just know that allows us to sort of fix this. And this then matches this example 2.6 from the Banks book. And I just want to show you that you can also do this example in a simple spreadsheet. So, and it looks very similar to what we did before. These are our inputs. The things that don't have any formulas, those are our inputs that come from input models. So the interarrival, we imagine those come from a distribution. I could provide you those numbers, but once we learn how to draw random numbers, like we're going to start talking about in the lecture C2, then you can imagine putting a formula in Excel where every time you open the spreadsheet, it actually draws different random numbers that come from the same distribution. So every time you open Excel, you get a different output from the simulation. Similarly, service times, these are numbers that I can just provide you ahead of time. That's what makes them inputs. But if I gave you the distribution, if I said they all come from an exponential random variable with a mean of 4 minutes, then I could ask Excel to generate random draws from an exponential distribution with mean of 4 minutes. And every time I open Excel, I'll get different numbers there, but they'll all be roughly around the same the values because they all come from the same distribution. That's what we mean by inputs. So the real inputs to the system are not the callers, although our stakeholders might view the callers as inputs. The real inputs to our model are these distributions. And then the outputs are whatever timing we get that comes out of this, the delays. So I put those in there. So how do I populate this spreadsheet now that I've got the complication of I have two servers in this dispatching policy? So I just want to show you how to modify that just so we can generalize this idea and then try to imagine if you wanted to create a network of these things, how feasible would it be to continue this process of implementing it all in a spreadsheet? So like last time, we said that the arrival time is just the accumulation of interarrival times. So it's just the previous arrival time plus the interarrival time. Arrival time 5 here is the previous arrival time 2 plus the interarrival time 3. 2 plus 3 gets me that 5, and I can 5 plus 2 gives me 7, 7, 2 is 9, and so on. So this is just a cumulative sum of this column. Now, the server here. So this is another one of these magical things with these spreadsheets, is that when you fill them out, the relationships will not be able to be calculated as you're typing the relationships in, but that's okay, because you just have to trust that once you fill out all the formulas, that there will be enough information for the spreadsheet to figure out the numbers and it'll all snap into place. So at this point, even though I haven't figured out any of the rest of the spreadsheet, then I just start putting in these relationships that capture what I know that must be true once this simulation is complete. And so this Abel versus Baker, what I've done to capture this dispatch policy is I just sort of say, when will these servers next be available? And so that's what this when server available to. At what time will both of these servers be available? And so initially they're both idle, so they're both available at time zero. So I'm going to start them at time zero. But then generally the formula here is I'm going to say that the server chosen, which is this column down here, is going to look at these two and then say which one of these times is earlier. So that's what I'm saying here. So that if I choose Abel as the server for this customer, this caller, if Abel's time is before Baker's time. So if Abel will be available before Baker, then this caller is going to get Abel. Otherwise, if Abel will be available after Baker, then this caller will get Baker. And these are all filled in, but that's because I've masked off a complete spreadsheet. When you would do this initially, then like basically it might imply that all of the, when you do this this inequality, either Excel is going to give you an error because it doesn't know how to compare two blank fields, or it's going to load those blank fields up with implicit zeros, and then it'll basically put Abel down all of this until you fill out the rest of it. And that's okay, because it's not supposed to be right as you go, it's supposed to be right after you fill everything in. So this is how I'm implementing my dispatch policy, is I am going to somehow have to manage this when server available column, and then I'm going to use the comparison of these two times to figure out which server this caller is waiting for or gets immediately put into. All right, so any questions about that? It might become clearer as we go forward. Okay, so I do need to figure out a way to populate these. So I'm going to start by filling down this column of time service begins. And so this is for this caller, when did their service begin? And I think what is always true about that? Well, for some callers, they get directly into a server. So their service beginning is going to be their arrival time. But for other callers, if they arrive and nobody is available, both Abel and Baker aren't available, then they're going to have to wait until that time. So that's what this max is doing. It's saying, let's look at when that caller arrived, and then let's then take the minimum of these two, the minimum of when Abel is available and when Baker is available. So that's the soonest you can get into any one of these two servers. And we take, if that happens to be earlier than the arrival time, then the arrival time, you can't start your service before you arrive. But if this is later than the arrival time, then this caller is just going to have to wait the difference between these two, and their service is going to begin at this minimum here. And then I have to say, well, then when does service complete for both servers? Well, for Abel, I can say, well, for this caller, is Abel servicing this caller or Baker servicing this caller? If Abel's servicing this caller, then I know that all I need to figure out is take the time that service begins and add this caller's service time to it, and that's when Abel will be done. If Baker's servicing this caller, then it's that way around. It's the same thing. You take Baker's service completion time, and that's going to be whenever the service began for this caller plus this caller's service time. And so I'm going to have to do that for both Abel and Baker. So in this case, if Abel's chosen, it's like I said, it's whenever this caller's service began plus this caller's service time. But if this caller, because this is an Abel column, if this caller was selected to go into Baker, then in that case, nothing changes. And so the next service completion time is just going to copy down whatever was in the row before it. And so then likewise, I do kind of the symmetric thing for Baker. So for Baker's next completion time, it's just going to be, if this is a Baker customer, a Baker caller, it's the Baker's begin time plus the Baker's service time, and that gives us Baker's time. Otherwise, if we're in the Baker column and it's an able customer, then we just copy down whatever the previous Baker completion time is, because nothing's going to change. Yeah. Our dispatch policy is choosing them. So that's a great question, is that if I go back to this column, this is the logic behind that. It's going to look at when they're available. And so if able and Baker are both available simultaneously, it defaults to able due to the less than or equal to. But otherwise, it's whoever is available first will get the caller. And that is modeling this dispatch policy here, where if you have one customer and two idle servers simultaneously, it goes to able. Okay. So we got able and Baker, so we're almost done. So now we know when their service time is going to be completed. So we know when the server will be available forever at every customer point. So we can now go back. We know when it's going to be complete. So we implicitly also know when they're going to be available. So say, when is able available? Well, just look in the previous row. When is their next completion time? So for customer 3, we can ask, when customer 3, you can think of it as when customer 3 arrives, when will able be available? Well, we know that in the previous row for customer 2, we figured out that able will be available at time 4. So for this customer, that's the soonest that able is going to be available is time 4. So we're just copying this row, this 4-5, that gets copied down here. This 7-5 gets copied down here. So we just shift the completion time down, and that gives us the when server available time, which is what causes the server chosen to lock into place. So we do the same thing with Baker being available. And then at that point, it's all response variables and statistics. So those are the only columns left. So we've actually done all the dynamics of the system. So now we can just run statistics on every caller, which is how long, how much did they have to wait in the queue, and how long were they in the system total to begin with, or completely. And so how long did they spend in the queue? Well, that for every caller, that's just whenever their service began minus their arrival time. So I know that for every caller. Those are columns. There's their arrival time. There's when their service began. And then how long were they in the system? Well, it's a different difference, but it's the same sort of idea. Here, you could say, well, for every customer, their time in the system is when was their server done with them. So if this is a customer who is put into the able server, then we say, when was able's next completion time for this customer, and then subtract this customer's arrival time. That is how long in total that customer was in the system. Likewise with Baker, and then that populates that column. So that's how we can simulate an MM2 queuing node with a spreadsheet like this, just modeling simple relationships. So any questions about that? So you can imagine behind the scenes, if you were to draw a bunch of queuing nodes and connect them together. So let's say once they're done with able, then they go to another queuing node that maybe is an MM1 queue, and then another queuing node, and so on and so forth. This is a pretty automatic process, and it's pretty modular. So if you know what type of queue it is, then you can kind of imagine, that you know sort of the structure of what this is going to look like. And an automated process could automatically create these sorts of things and then string them all together and then try to simulate the outputs of a complex network of these queuing nodes. But that would be a real headache if you were to do this by yourself. Like, if you were to manually do all these sorts of things, then if you wanted to make a change, like, actually, I don't want this to be an MM2, I want it to be an MM1, or maybe I want it to be an MM4. Well, it'd be really annoying. Like going from 1 to 2 was bad enough, but going from 1 to 4, then you're adding extra columns. You have to make sure you got the logic right of who's selected, and it would be a real headache to try to do it by yourself. And so, again, you could automate the construction of these, but doing them by hand would sort of be not so great, which is why we have programs like Arena, which effectively are automating the construction of these sorts of things behind the scenes and doing all this work for you. So all you have to do is draw the diagram, which gives you the structure, and then give it the distributions for the input models, which gives the numbers to put down through the inter-arrival times and the service times. So, many types of dynamical systems can be simulated in the spreadsheet. Certain sponsors, I mentioned this before, are going to ask you to use tools like spreadsheets that are approved for use inside their agency. But small changes in the system structure, like changing the capacity of a server, can require significant coding changes. So it's sort of a headache to think about doing a complex DES inside a spreadsheet. But what we want to pivot to today are some other types of simulation that are pretty well suited for these spreadsheets, and I think also are nice because they require some statistical analysis that it's a little easier to embed within the spreadsheet framework, and that's particularly Monte Carlo simulations, and that's what we're going to talk about for the rest of today. But I wanted to give this example to motivate why we have to go out of tools that we've seen before into tools we've never heard of before, like Arena, FlexSim, Simio. It's to simplify this ugly process, which otherwise is pretty robotic. It's just there's a lot of opportunities for mistakes if you're to do it yourself. All right, so any questions about these examples, the MM1Q and the MM2Q in a spreadsheet? Okay. All right. So more things that we can do with spreadsheets. So this is like, inventory management. This is something. So these are examples, a lot of examples that I borrowed from the book that we can kind of go into more details here. But inventory management problems, these are problems where you're trying to figure out how much inventory do I keep based upon how frequently do I think that inventory what the demand for that inventory is, and how quickly I can resupply that inventory is a set of these so-called inventory management problems. And so in these types of problems, we usually do have events, but they occur like the muffin simulation at regular non-random intervals. So every day you can assess your inventory. Every day you can make an order for new inventory. Every day you can say how many people are going to ask to buy a certain amount of product from me. So those are the types of things that each interval, every day, every hour, each minute, there's some quantity demanded, which you can imagine is just drawn randomly from a distribution. Again, very much like the muffin baking simulation. So in that particular case, we know every minute a certain number of muffins arrives to be baked. We just don't know how many muffins. And that, in effect, is an inventory management system. What's the inventory in that system? It's the space in the oven. So having a very, very large oven is going to take up a lot of space on the floor, which might mean you have to pay more rent because you got to, break out a wall and take over the store next door. And so that's effectively, an inventory of space. But are you using that space? And that has to do with what demand is there. And if only 2 muffins arrive every minute and it takes 3 minutes to bake them, then maybe you don't have that many muffins backed up and you don't need that many muffins in the oven. So in that case, a smaller oven would be better. Well, that's like saying, if I'm selling soccer balls or something like that, how many soccer balls do I keep in my inventory? Well, it depends on how many people want them every day. And if not that many people want them, then I probably shouldn't stock hundreds of soccer balls in a warehouse somewhere, because that's going to take up a lot of space and I could be stocking other things. So that's really the question about inventory management, is how quickly can I get more inventory? So in the muffin case, the baking, that is a model for how long it takes to, order another soccer ball. Like it takes 3 days. Well, it takes 20 minutes for me to free up space in the inventory. And then what's the demand? How many people come in? How many soccer balls are sold a day? How many muffins are arriving at the oven a day. So that lab two, the muffins space was exactly an inventory management problem. It was just sort of phrased as something a little bit different than that. So more generally, in demand carries over from period to period. So if you have a demand for 3 soccer balls in period 1 and you only can supply 2 of them, well, now that extra 1 goes over to the next period. And so decisions are based on your current inventory or unmet demand. So how many, like we've had 100 soccer balls sitting here in inventory for the last month. Should we really order more soccer balls? Probably not in that case. But if we have back orders for 50 soccer balls, then we probably should fill those orders because we're not actually going to get paid until we fill those orders. So in that case, whereas we normally would order 100 soccer balls, now we're going to order 150. So those are the types of things we're trying to figure out. Not knowing exactly what demand's going to come in the door the next day, the next hour, the next minute. How do we buffer against that and put that in our inventory? So these systems do have state. The current inventory level is the state, and they require dynamic simulation models that keep track of that state. So that's what we can build operations research models for. Now we can use assumptions to simplify these models to make them functionally static. Now, what do I mean by that? We can, for example, convert end-of-day inventory into a cost and then start over. So that way we don't have to carry. We actually don't carry the amount of soccer balls over to the next day. But we can say that there's a certain cost that day generated, and then the next day is going to generate another cost, and the next day is going to generate another cost. And if we average over all our days, then we'll get an average cost generated per day. And so the days don't interact, but they generate contributions to cost that we take statistics over. So that's one way that, that's much simpler to implement than these models. So that's just one sort of example here. So one of the classic inventory management problems, to make this a little bit more concrete, is the so-called order up to problem, where there are 2 decision variables. So in SIMS or in operations research, we usually have decision variables, which are the parameters that are not fixed. Those are the parameters that we're optimizing over. And we have 2, M and N. So capital M is our target inventory level to order up to. So every day you look at your current inventory, and if it's under M, then you can order up to that amount. And I say every day, but we can choose how long that period is. And then so N is how often to review that. So is it every day? Is it every 14 days? Is it every month? And those are your 2 decision variables. So it's basically saying, imagine an inventory manager comes by every Monday and checks the inventory. And if it's under this dashed line, then orders up to that dashed line and then doesn't come back until the next Monday to do that again. That's the so-called order up to problem. And so given a certain input variable, like given demand and order lead time. So demand distribution. So this will be a distribution of orders per day. So some days people order 1, some day people order 4, some day people order 2, but on average they order 2.5, and it comes from a certain distribution. Likewise, the lead time. So when you order, how quickly does the replenishment arrive? That's the other thing that we need to know, and that can be a random variable. So when I order 5, sometimes 5 items come to me the next day, but sometimes 5 items takes 3 days to get to me. So I need to maybe have a distribution there. So these are 2 random distributions that we're going to use as inputs, and then our goal is, facing these as challenges, what is the best response in these? That's the order up to problem. We want to solve that problem. So any questions about that basic idea? All right, so in the book version of the order up to problem, they model refrigerator sales. And then later in lab 7, there is a little s big S inventory problem that is very closely related to the MN inventory problem. So we'll see this again. In their model, inventory is a state variable. So how many refrigerators are in your inventory is your state variable. Every N days, they order enough refrigerators to bring it back up to M units. orders take several days to arrive. And each day there is a random number of customer refrigerator orders. So how often do customers come in and ask for refrigerators from the inventory? Now, they model the lack of inventory as back orders or lost sales. And so if a customer orders a refrigerator and it's not there, then that's accounted for effectively by a cost. So that's, we either view the opportunity cost, the lost sale, as a cost, or we view back orders as, even though we've got the sale, due to the interest on that, because they don't actually pay us until we don't send it to them, then that every day that's on back order is a cost to us, because that's money we could have had if we just had the inventory available, but we don't. And so the other costs we have to worry about is having too much inventory. So you pay rent for all that space that the refrigerators are taking up in your inventory. You could put other products that might have better profit margins in the space where you're storing refrigerators. So having refrigerators at the end of the day is also a cost to you. So you pay two costs. You pay a cost of not having enough refrigerators, and you pay a different cost for having too many refrigerators. So ideally, those things would be perfectly matched. You wouldn't keep any inventory. You start the day, somebody would deliver 5 refrigerators, someone would come in that day, they'd buy 5 refrigerators, you go home, 0 refrigerators in inventory. The next day, another 4 refrigerators show up, people buy the 4 refrigerators, and so on. That would be the ideal case, but that'll never happen. So how do we deal with the realistic case? So the way they modeled this, and they used a spreadsheet to do it, is they have input models like we've been talking about here. So rather than having strings of demand, so Monday's demand, Tuesday's demand, Wednesday's demand, like we did in the homework, they have parameters on distributions. So they're saying here that this is a discrete probability mass function, where we're saying that every day, daily demand, you can either order, or there's either going to be enough customers for 0, 1, 2, 3, or 4 refrigerators. And these are the probabilities of each of those possibilities, those outcomes. So there's a 10% chance that nobody's going to want a refrigerator today. There's a 10% chance, roughly, that there's going to be 4 orders today for refrigerators, and so on. And so for technical reasons, which we will talk about when we talk about generating random numbers, they turn this probability mass function into a cumulative distribution function, which is just, you take this and you sum everything together. So it all ends up rising up to 1. And that ends up helping them generate their random numbers. But the real inputs here are these things. So your stakeholders will give you this probability, or you'll go out and model it. You'll go and sit at Best Buy and count how many people order a refrigerator each day, and then you'll end up, coming up with this distribution. And then there's lead time. So same idea. They modeled it as a discrete probability distribution, where when they order new refrigerators to come back in the inventory, it's either going to take 1, 2, or 3 days for them to get back to them. Most of the time, 60% of the time, they get it the next day. 30% of the time, it takes 2 days, and 10% of the time, it takes 3 days. So, so those are those things there, and these are what we refer to as the input models of this system. So that's how we model those, the probability distributions. So they're going to put that into this giant spreadsheet, and I'm not going to go over all of the the details of how they set this thing up. But basically, it's very similar to these, like, if it's coming up with relationships like we did in that previous case. So you've got days down this side here. Then you've got these different state variables that they call step, but step is kind of a sort of a special type of state variable. It's got these state variables, which are sort of like what our current inventory is, and then there's these, for technical details, how they manage these cycles here. But the big thing you focus on here is the inventory, and then in the input, the demand. So this is our beginning inventory that day minus the demand of that day. This is an input. So these are random numbers drawn from that distribution. And then if you do 3 minus 2, this is our ending inventory. So most of the time here, you see that there's positive inventory, but occasionally there's 0 because, like in this case, the beginning inventory was 0, the demand was 2, so that's going to generate back orders. So you can see those back orders being accumulated here in this shortage quantity. So at the end of the day, they know how many refrigerators are in the inventory. They know how many back orders are there. So they can use these things to calculate costs. So how much are we charging ourselves for the refrigerators that are sitting, and how much are we charging ourselves for orders that were not able to be filled? And then so that's what they're kind of keeping track of all this. And what this all ends up to is being able to generate a distribution like this. And so this is a histogram of the 25-day average ending inventory. So this is simulating over 25 days. And here's my ending inventory, and they took an average over that 25. So you could take this and run this a bunch of times. So I don't know if it says here how often they run this. So if you added these numbers up, 9, 41, 42, and 8, so it's like 100 times. So they basically ran that spreadsheet 100 times. So it's like they opened Excel 100 times, and then they looked at what this number was down here, and they got 100 of these numbers. So every time you open Excel, it's going to generate new demands and new lead times. So here's the lead times here. And so those two things, every time you open Excel, you get different numbers there that come from that distribution that we trust is modeling reality. And that's going to give us a different number down here. So you're going to get 100 of these numbers. And you take those 100 numbers and you put them into a histogram. And this here is a spread of your average ending inventory. So some days you have only 2 refrigerators in your inventory. Some days you have 5 refrigerators in your inventory. On average, it's somewhere in between 3 and 4 refrigerators in your inventory. So, but it doesn't just give you the average, it gives you this spread. So if you wanted to know, how much space do we need for our inventory for our refrigerators, this suggests that if you have enough room for 9 refrigerators in your back room, then you're probably fine. You probably don't need to make room for more than 9 refrigerators. In fact, you're probably going to be fine with 7 refrigerators. That's something that the average models, so a lot of what you'll do in 470 is about averages. And you could say, yeah, I might know the average number of refrigerators that I have every day. But if I don't know that spread, then that doesn't help me on a day-to-day basis with planning, because I need to know, is there even going to be enough space for me to keep that amount of inventory? Because if I only have enough room for 4, for example, then that's going to wreck this simulation, because I'm going to generate even more back orders because I ran out of space to order up to enough refrigerators to meet my demand. So that's why it's useful to have these distributions have variance and not just averages. So that's kind of one example of that, and I'll kind of elaborate on that. But any questions about this basic idea here, that we generated a sim of 25 days just to generate an average, and then we generated 100 averages to get a distribution, and that distribution gave us insight into how we can shape the space of our inventory. And something that I need to go back to the whole point here is that the MN, like this, by the way, was set for a particular MN policy. So the next step would be to try different MN values, order up to values, and inventory inventory checking periods, to see how it affects this and how it affects the costs that are generated. So I'm not showing that process, but this is just for one iteration, for one choice of decision variables. So if you choose a different MN, then this distribution is going to change. If you choose a different MN, then the distribution is going to change again. And then you have to figure out, well, what's a better distribution? So if I'm trying to minimize space, if I want to maintain the fewest number of back orders with the least amount of physical space, then you could imagine iterating over those different MN policies. Maybe I need to check my inventory very, very frequently, and I need my order up to be a small number. So an M and N both to be really small, and maybe that will shift this distribution over so that I don't have to keep that much space for refrigerators, because I have kind of a just-in-time ordering scheme where every day I can order. But if I have a lot of space, then maybe that does give me the freedom to only check my inventory every week, but because I can order a lot of them and just keep them in inventory. Okay. So the other classic inventory management problem that I want to show you, because it gives us a more direct juxtaposition of averaging methods like you see in 470 and our sort of more variance methods that you see here in the sim course, is the so-called news vendor problem, which is also the single period or perishable inventory management problem. So this is a simplified case. Imagine that sort of the cartoon of as like in an old movie, somebody standing out on the corner selling a newspaper. They have a certain number of newspapers that they want to sell, but that news is worthless the next day. So anything they have left over in their bag at the end of the day has to be thrown out. That's the news vendor problem. So the idea is you have uncertain demand. You don't know how many newspapers are going to be sold that day. There's fixed prices. So, those newspapers, you have a sort of a consistent newspaper price on how much it costs to produce the newspaper and what you're selling it for. And so it's not like they get cheaper at the end of the day. And then it's a perishable product. And so it's worthless the next day because that's old news. So, of course, this doesn't only apply to newspapers. It also applies to certain produce items, for example. So things that are very, very perishable. So you can't resell them if they haven't been sold by the end of the period. So there's no state to worry about here. That's the beauty of the news vendor problem, is that you don't carry anything over from day to day, unlike the last problem that I showed you. So in the inventory problem, the kind of lazy way to solve this problem is to just do everything based on averages, like you would do in 470 for a lot of the problems. And so the idea there would say, what is the average profit I get from my inventory choices here? So the idea here is that if I want to model the average profit, well, that's going to be if I look at my inventory and my demand. So the demand is a distribution here. So that's like, I model how many newspapers people want a day, and that comes from a distribution. Sometimes it's 5, sometimes it's 2, whatever. And I can then say, well, how much inventory am I carrying with me? And that's what I want to try to figure out. Well, I can say, well, if the minimum of those, like if I only have 5 newspapers to sell, that's the most profit I can make is going to be 5 times the sale price. But if I have 100 newspapers here, then the most I can make is limited not by my inventory, it's limited by the demand. So I see which is limiting, my inventory or the demand, and I multiply that by sale price, and the expected value. Basically, all of this stuff is you can actually solve for this, like for relatively simple demand functions like normal distributions. You can plug this in, and the expectation would of turning this into just a number. Like you mathematically can solve on with paper for this expectation, given this is the normal distribution and all the rest of these are just deterministic values. And then the cost. Well, the cost is how much did I pay for my inventory? So if I bought 100 newspapers, then it's going to be 100 newspapers times whatever the publisher charged me to buy those 100 newspapers to put in my bag. And then, that's going to subtract off from the gross revenue that I got. So revenue minus cost gives me my profit. So given a convenient probability distribution of demand, like a normal distribution or something like that, you can mathematically average. Basically, this will just become a formula that has a variable inventory, and you just do a little calculus on it. You take the partial derivative of your profit formula, your expected profit formula, with respect to inventory, you set it equal to 0, and you solve for the inventory star that optimizes that. And you're done. And that will give you the inventory decision that for this demand distribution will maximize your average profit. That's kind of the lazy and easy way to do this. This is something you can do in a half a page of paper in about 10 minutes of work. But it doesn't capture all of the things that we really care about. What if we need more than just average performance? What if we don't make $150 in profit each day, we're not able to, let's say, pay the bills? Like what if we have a threshold that if the daily profit goes below, then it means that we can't survive to even do business the next day or the next period? That's where the variance matters. It doesn't care if my average is 15, if my threshold is 10 and some days I make 6, then I'm not going to survive those days that I make 6 to live for the sort of law of large numbers to eventually get to the day where I make 15, 16, 17, 20. I can't depend on that if one day's worth of going under threshold is enough to kill me. So that's why I need to model variance as well. So what an alternative approach, and this is something that is done in the book here, is to build a little sim, and you can do this in a spreadsheet, where we model this as saying we've got a fixed quantity of newspapers we buy for resale each day. We have a demand that varies each day, just like before. If our demand is greater than what we bought, then we're making too few papers. It's a missed opportunity. If our demand is less than the quantity, then we've wasted by buying too many papers, so that's high costs. And so we can ask a question, how does the quantity of newspapers affect our 20-day aggregated profit? And our sim then will not just give an average, it'll give a whole distribution. So they do that. They basically say, well, what are the input variables here? Well, some days it's going to be a good news day, a fair news day, or a poor news day. So this is going to be kind of an interesting thing. We actually put a distribution on a parameter, because what we're going to do is we're going to say, okay, we actually have a demand distribution whose parameter, who's got like this, like the quality of the newsday parameter, which itself comes from another demand distribution. So we're chaining together random distributions here. So we don't know what type of news day it is. So it's, a day after the debate. Maybe that's a fair news or a good news day. But maybe, your average Monday is a fair news day. And then your average Friday is a poor news day. Nobody's reading the news on Friday. Everybody's reading the news on Monday. And if there's a special event, then that's a really good news day. But those don't happen that often. So the most frequent news day is this 0.45. So what they're saying here is, if you happen to be on a good news day, you're going to use this demand distribution. If you happen to be on a fair news day, use this demand distribution. If you happen to be on a poor news day, use this demand distribution, where these are the probabilities for these orders. Question? Oh, I haven't gotten to that yet, but that would be something that would be specified, to you. If, for example, it might be that in order for you to pay for gas, for example, so you always have to cover your variable costs in economics and microeconomics. And if your variable cost of doing business every day is the cost it takes to drive around the city, and if it costs you, let's say, $20 to drive around the city, if maybe if you don't have that $20, then you're not going to be able to actually buy gas to do business the next day. It's a little contrived example because, $20 or whatever, but if you scale this up to think of a major organization, then you might be talking about like, well, we need to make, $100,000 each day to put 100 trucks on the streets or something like that. And we just don't have the credit to buy into credit to keep those trucks on the street or something along those lines. So there are a bunch of these cases, they're like in animal behavior, for example, like, there are animals that if they don't generate enough calories during the day, they won't survive the night. And so there are these examples from natural and for engineered systems where you do have these thresholds, and your goal is not to maximize your average. Your goal is to minimize your probability of going under threshold. Now, it might mean that if you're under threshold, there's still some probability you'll survive, but it's extremely decreased. Your survival above threshold is guaranteed. Below threshold, you start playing the numbers. And speaking of playing the numbers, this is a huge amount of complexity that we've added here. We've chained together these distributions. And so, this is something, again, that our little back of the envelope model is nowhere near this, right? So we've got this cool demand distribution stuff. We can then generate a spreadsheet here, which basically tells us for every one of these days, for 20 days, what's our revenue from sales. So we have this is for 70 newspapers. So this particular output is saying, given that we're just going to buy 70 each day, then we've got the demand distribution, which depends on the news day. So we draw the news day for every day. We draw the demand for that type of news day that day. From there, knowing that we bought 70 newspapers, then we figure out what the revenue from sales is. That's demand times how much we get from each newspaper. The lost profit from excess demand. So how much opportunity we lost by not having enough. The salvage scale from scrap. So here we've even added a salvage value. So we're saying the newspapers, even though they don't have any news value, we can give them to a recycling joint and they'll pay us a cheap amount for them. So we get a little bit of salvage out of that. That's something you definitely don't have in that simple back of the envelope model. And then it gives us a daily cost, a daily profit, and then we get a total profit over 20 days. And so now we can average this, over this sort of 20 day, and we can get a distribution. So this here is the total 20-day profit. So what we did is we ran this for basically whatever 10 plus 78 plus 145 plus 129 plus 34 plus 4. So that's how many times we opened the spreadsheet up and had it generate new numbers. And for each one of those, it generated that 20-day profit number. And sometimes it was up here at 200. Sometimes it was down here at 80. So it has an average. And so if you do a back of the envelope model with expectations, that is what you'll describe if you can manage to deal with all of the complexities that we've added, which already it's probably not analytically tractable to do. But as you can see, the average doesn't tell the whole story. If you did have this minimum performance threshold, then even though most of the time you are above that threshold, there is still sometimes you're below. If it is really, really bad to end the day below that threshold, you often will make choices that reduce your average in order to also reduce your variance. It's a little bit like a bet hedging. So, you could say that I might choose a different Q value, a different quantity of demand, and it might mean that my average performance is lower, but the probability of going under that threshold might now drop to 0 as well. So maybe the only way to squeeze this distribution in is to accidentally shift it over to the left. The other side of it, like a lot of times I mentioned that these inventory management problems also sometimes relate to financial problems. What happens if your distribution is on the left side of this performance curve? What if almost all of this curve is over here? In that case, it would be great to increase your mean here, but in that case, your actually main goal may be to increase your variance. And so that's what we call a stretch goal. So if you have a system that has random outputs, stochastic outputs, and it's always in the mean of that system is under the performance threshold, then in that case, you actually make optimization choices where you optimize variance, not average. So here, if you can maximize your average, and that will, as a heuristic, tend to move things away from this dangerous period. But if this whole distribution's over here, you might switch your objective to maximizing variance. So it's just like if somebody says, you're at a game show and they say, this envelope's got $500, this envelope either has 0 or 1,000. If your rent is $200, you take the $500. If your rent is $750, you're screwed if you take the $500. So you might as well take the 0 or 1,000, because if you're 0, you still can't pay rent. But if you're 1,000, you at least have some probability to pay rent. So depending on what your threshold is, that changes your optimization objective. Do I maximize variance or maximize mean? So that's why knowing this distribution can be so much more valuable than just knowing the mean. And that's one of the things that these sims give us. All right, so are there questions about that? Okay. All right, so basically what that leads us up to is this method that you're going to then play with in lab 3, the Monte Carlo method. And so this is an example of a stochastic simulation that uses random sampling to try to estimate a quantity that is impractical to calculate exactly. In the lab 3, pre-lecture notes or slides, we'll talk about how some of the earliest examples of doing Monte Carlo estimation were things like estimating pi. You can throw darts at a dartboard and use the locations of where the darts land at the dartboard and count them up. And if you count them up in the right way, you will estimate pi to as many digits as you like. You don't have to measure the circumference of the dartboard and divide by diameter or whatever. You just throw darts at a dartboard and count up where they land, and you will be able to estimate pi. And that's an example that we'll talk about, or they'll go into the lab. And you can, this method actually first came up when they were developing the atomic bomb. They had to come up with a code name for this method, and this was the code name that they came up with, so that it would disguise what they were doing. Monte Carlo relating to gambling, and gambling related to drawing these random numbers, and they needed to estimate a bunch of parameters numerically, and all of the methods at the time that were deterministic were taking way too long on a computer. And so people like John von Neumann figured out that you could randomly sample in a special way to estimate numbers, and you could do it very, very fast and get very, very precise. And that's the type of stuff that we'll talk about in Lab 3. So an example application of that, that isn't quite just that isn't exactly, I mean, you could argue this is estimating a number, is, let's say I'm trying to do a operations research problem for a military context where they are dropping bombs on an area that is outlined here. And it could be bombs, or if you don't like that, it could be food packages. The whole point is you're dropping things that have a dispersal spread. They spread out. And then the question is, what is the distribution of the number of bombs in this mission that reach the given target area? And so all I know is that for every one that drops, even though I dropped it from here, it could land anywhere in some distribution. And I want to know that if I drop 20 of them, then what's the distribution of the number of them that actually land where I want them to land? And so how might I do that? Well, this is because of the weird shape of this here and some of the distributions we might choose here, it might be impractical to solve this thing using math. So instead, I use a Monte Carlo simulation of 10 bomb mission runs. And so basically, I go into a tool like Excel or MATLAB or R, and I say for every simulated run, I generate 10 simulated positions of where bombs land. And so I know that if I drop a bomb here, there's a distribution of where it's going to land. So I can draw 10 of those, and those are where those 10 bombs landed. And then I can take that, and then I can say, well, how many of them landed within my geometrically defined weird area? And that'll say, for this run of your 10, 6 landed in it. For another run of your 10, 4 landed in it, and so on. So then I do hundreds and hundreds of those samples, hundreds and hundreds of those runs. And then I say, what is the distribution? So basically, what is the average number of bombs that landed in that area? And I'm estimating effectively a probability here. And that allows me to calculate sort of like for this policy, what would I kind of expect on average there? And so I might get a distribution like this. So that means sometimes only 2 hit it, sometimes all 10 hit it, but most of the time it's somewhere in between here. So that's my distribution for the number of bombs that actually land in that weird area. And that's a Monte Carlo sim where every simulation run is a single row, and we generate a huge number of rows, and then we look at the distribution across those rows. It's sort of a simple example. So questions about that example, what we kind of did there, and that is an example, again, if you want to see how that's done, it's just from section 2.5 in the Banks book. All right, so then, another nice problem here, reliability problems. So we have a machine that has 3 ball bearings that if any one of them fails, it causes the machine to fail. So each one of them have a failure time distribution, which is the time until the next failure. So we know that maybe across all of them, on average, they have a 10-hour lifetime or a 1,000-hour lifetime. But in reality, sometimes it's a little less, sometimes it's a little more. And the problem is whenever one of them fails, the whole machine's taken down. So one of the questions would be, do I replace them all individually, or do I, whenever one fails, replace all of them, because the other ones will probably fail sometime in the future, and I may as well just take the machine down once, even though if it means wasting the life that are left on those other ball bearings. That's kind of the question here. So how does a replacement schedule affect operational costs? Again, impractical to solve this based on formulas, so I run a Monte Carlo experiment. And so I simulate 15 three-bearing sets for two different policies. One of the policies would replace each ball bearing only when it fails. The others replace all three ball bearings when any one of them fails. And so, 15 rows, and in each row, I'm going to have, three ball bearings. So, when do those ball bearings fail? So that's basically what I mean by three. And then I am then going to use those failure times to then say, under one policy, what is my cost? Under the other policy, what is my cost? So I simulate both policies. In each row, I draw a lifetime of each of these 45 ball bearings. That's 3 times 15. And then I also draw the delay until a mechanic arrives, because that's really costly. Every minute the machine is down, that's the cost that I'm paying. So if I know the cost of the lost opportunity cost from that machine being down, that gives me a cost of these policies. It's the cost of buying the ball bearings and the cost of waiting for the machine to get repaired. And I can put that into a spreadsheet, and I don't have the results here. I'm just kind of explaining roughly how this would be done. And then from there, I can compare, kind of like the greedy simulation policy versus the nearly full. I can compare the two and say, well, if there's a huge delay until the mechanic gets there, then it's actually better for me to eat the cost of the ball bearings and just replace them all right now, because I can't pay that delay. But if the mechanic is on staff and can arrive really quick, pop a ball bearing out and pop it back in, then in that case, maybe I just do one ball bearing at a time. And that way I get the full lifetime out of these ball bearings. So if the cost of the ball bearings is high, then one at a time is going to eventually dominate. If the length of time to replace the machine is long, then replacing all three will make sense. And this gives me an idea, a quantitative idea about where that point is that I switch from one policy to the next. Now you're going to get a distribution for this policy and a distribution for this policy. So to compare the two policies, I can't just compare means. I have to use something like a t-test to say, is there a significant difference between these two? And if the t-test says t less than 0.05, then I say, all right, which one is lower? And I'd say, well, if the cost of A is lower, that is statistically significant. It's a significant difference. So I'm going to trust that that's actually lower. If the t-test comes back and can't tell the difference between these two, even though I've run a huge number of runs, then I'd say, it doesn't really matter. And I will let management make the decision based on other factors that aren't modeled here. All right, so this is the lab 3 activity that I wanted to kind of show to give kind of an explanation of what's going on here. And you'll get this again in lab 3. But this is a stochastic activity network. And so the model here is making breakfast, but it doesn't have to be breakfast. But it's just, if you have an activity that has multiple parallel paths that each have different stops along the way that take different amounts of time, then the question is, how long does the total task take to finish, and which path was the limiting path? So basically what I'm saying here is it's going to take a certain amount of time to go the top path, the middle path, and the bottom path. And sometimes the top path will take the longest. Sometimes the bottom path will take the longest. Sometimes the middle path will take the longest. Whichever path takes the longest is going to determine how long it takes in that iteration for the activity to finish. So, in this example here, we say, what if the top path is, we're making breakfast, and there's 3 things people have ordered for breakfast. They've ordered eggs, toast, and bacon. And in order for me to make eggs, there are 3 steps that I go through here. And each one of them take a small amount of time. So to go step A, that's a uniform distribution between 2 minutes and 4 minutes. Going from A to B, that's a uniform distribution from another 2 minutes to 4 minutes. B to finish, uniform distribution from another 2 to 4. So an average 3 minutes, 3 minutes, and 3 minutes. So on average, this top path takes 9 minutes. Toast only has 2 steps. Get the toast out, put it in the toaster. And so this step we're saying takes between 3 and 6 minutes, average of 4.5. This takes between 3 and 6 minutes, average of 4.5. So the average time for the middle path is also 9 minutes. And then down here, we've got bacon. Well, in the bacon, there's 1 step to make the bacon. It just has to cook. And that takes 9 minutes on average. And so they all take an average of 9 minutes. but they're all randomly distributed. So the question is, if they all take an average of 9 minutes, then is it just like a uniform distribution, which one ends first? Or is it going to be that one of the legs tends to finish more often than another one of the legs? And then spoiler alert, that will be the case. And so what the other thing I'm hoping you to see in here is that the other downside of just looking at averages is there are these weird distributional effects that happen. When you sum distributions up, it changes their shape. So everything here started uniform. Well, what we're going to see is that the distribution down bottom is going to stay uniform, but the distribution up top, the sum of three uniforms, is not uniform. And that is going to change how often the top is the longest versus the bottom. That's what you'll see in the lab. And so that's kind of, this is sort of the hint. These are the types of things that I'm expecting you to see in the lab, that this top distribution is going to look more like a bell curve. And hopefully you remember why a sum would tend to look like a bell curve when you look at its distribution. There is a famous result that hopefully you remember from 380 or 385 that explains why a sum of uniforms should look like a bell curve. But then when you put that in together, when you compare the bell curve to the uniform, then you have to ask, well, how often does the top distribution take a long amount of time versus the bottom distribution? And I think, and I'll let you sort of work this out in the lab, but if you start looking at it here, then I think you hopefully get a hint at which path is going to be more likely to take more time and how that will affect your result. So that's kind of what we're doing here on Lab 3, and you're going to do that by generating a Monte Carlo sim of this activity network. So in every breakfast row, that's every run of breakfast, you're going to generate 3 random numbers for eggs, 2 random numbers for toast, 1 random number for bacon. And then you're going to ask, what's highest? The sum of the 3, the sum of the 2, or the 1? And from there, that highest number will represent how long breakfast took that day. And you're going to keep track of which activity, eggs, toast, or bacon, took the longest. And you're going to do that for a bunch of different days, for a bunch of different breakfasts. And then you're going to take the distribution of those average time, or those total times. And then you're also going to look for a distribution across the 3 different activities. And then so you can see which activity tends to take the longest and try to figure out why. So that's what we're doing in Lab 3. So any questions about that sort of preview of Lab 3? Okay, so the last thing that I then want to comment on, and then I'll give you your clicker question and get you out of here. But so I talked about spreadsheet simulations or spreadsheets for this whole time here, and shown that they can be valuable in special cases. So why are we not just using tools that we're familiar with? Why do we have to pay for these proprietary ugly tools like Arena, FlexSim, Simio? Regardless of which tool you use, you'll agree that they're all bad. But somebody's put them together for us and as an alternative to this. So why do we use them? And it's really because we are doing research as industrial engineers, as operations researchers, on complex systems where you cannot predict the state of the whole system by just looking at a little bit of it. So you have to create giant networks of components and look at these network effects. And so, even something as simple as a drive-through, there are these questions like, do I do sequential windows in a drive-through, or do I do parallel windows in a drive-through? And this has already so many components that it would be really, really cumbersome to build inside these spreadsheet tools. And so, as you scale up to more and more of these problems, and you start thinking about all the additional complexities that modern technology adds, like ordering ahead, that's like a hidden line of orders that's coming in that has a totally different distribution. It's hard to get data on, and so on and so forth. And you really need a lot of flexibility, especially because these technologies pop up like, now, we've got AI tools, large language model tools that now you can't get away from them. Microsoft is now going to sell computers that constantly are taking screenshots of everything you do to try to better predict how it can help you. And it stores it all locally. And so, how is that going to change people's process flows? So we not only need ways to model complexity, but we also need ways to modify them easily later. And that's what these tools give us, a lot of that flexibility. And they're a little ugly to work with. But once you get used to them, then hopefully their benefits outweigh their costs. All right, so automate these tedious tasks. They include high-level components already pre-built for you. They have usually attractive graphical options, which your stakeholders are going to really like because they're actually going to look like real people moving through these systems. And but still, even though you get these cool graphical outputs, they're also going to generate data. And that's one thing that Arena, FlexSim, or whatever, they'll give you quick ways to preview your data, but they are not statistical tools. They're not very good at that. So ultimately, all the skills that you've built up using spreadsheets, using R, SPSS, SAS, using Python and Pandas, whatever your tool of choice is to do your data science, you can still apply. These will be data generators and these will be data consumers. And that's really the complementarity that we have in the modern way we do these sim studies. All right, but that's so that's going to be the case for agent-based modeling, for DES, and for system dynamics modeling. Great tools to make the modeling easier, but we've got data processing tools that help actually making sense of the data afterwards. And what we're going to start with next week is agent-based modeling. We'll start seeing more of that, and then finally we'll get into DES. So lab 4 will be about agent-based modeling, and then lab 5, that's when we actually start doing the arena. So I don't want to keep you any longer, so let's just do an iClicker, and if you have any questions, feel free to come up. So question I have. So question I guess I'll ask is, so if your performance distribution is on average below threshold, then should you maximize or minimize the variance of that distribution? So if you've modeled a system and the performance distribution is way below threshold, then is it better to choose to maximize or minimize the variance in that distribution? And that's all I've got for you.